Okay, so in the swim, bike, run competition, otherwise known as a triathlon, it's generally an endurance competition. It's one of those things where the person who is the most powerful, the biggest, the strongest, the fastest is not always the person that wins. And it's kind of the same thing whenever we talk about it in terms of work and power and physics. It's not the one that has the greatest force. It's not the one that moves the farthest. It's not the one that moves the fastest, but instead it's the one that's a combination of all those three things. And we're going to talk about that a little bit, but just so you know, whenever you push something that's really large, that doesn't necessarily mean you're the most powerful. Whenever you do something extremely fast, that doesn't necessarily mean that you're the most energetic. And we'll kind of talk about that as we go through. The first thing is physical work. Physical work is very, very different from the concept of work as you know it. Whenever you have a job and you say, hey, I'm going to work, that means a certain thing, but whenever you look at it in the context of physics, it could mean something very different. And here's what I mean. Physical work is the action energy that relates kinematics and dynamics with energy. Okay, physical work requires two things. You must apply a force on the object, and the object must move in that same direction. And this is why it's really important. If you were to look right here, you have the man, this is Sisyphus, if you know the Greek legend. He is pushing this rock, and if you look at it, he is clearly exerting a force on the rock. He is trying to push the rock up here. But we cannot classify this thing as actual physical work because we don't know if he's making any progress. If the rock were to move in that same direction, then yes, we could say that Sisyphus is in fact doing work. But without that movement part of it, we can't say for sure whether or not that he is doing work. Another example says, does a person leaning against the wall do work? So you have a person, and they're leaning against a wall, and they're clearly exerting a force on the wall, but the wall doesn't actually move. So because the wall doesn't actually move, you can't say that the object or that this person is doing any work on the wall. The next thing is you have to say that the force and movement are in the same direction. So let's say that I have a situation in which I am lifting a tray or a box, okay, and I'm clearly exerting a force on the box upward, okay, because I'm keeping it up out of the air. So I'm carrying a box or a tray. But my arm, which is supplying the force upward, is my arm. The box is moving this way due to my feet. So can you say that your arm is doing work on the box? And in fact, you can't, because the force and the direction are perpendicular to one another. Remember, you must have the force and the displacement be in the same direction in order for work to occur. So this is where we get the equation. The equation is work equals force times displacement, and we've talked about most of these before. We've talked about force as being a push or a pull. It's measured in newtons, and you can measure it with a spring scale. We've talked about D. D is really displacement, not distance. But on the formula chart on the tax formula chart, it actually says that it's distance, but really it should be displacement. But it is measured with a meter stick, and the unit is the meter. So one thing that you have to realize is, once again, this assumes that the force and the displacement or the distance are in the same direction. If they're not in the same direction, this formula will not work. So let's take a look at this formula in action. It says determine the work exerted on an object if it is subjected to the forces below for 10 meters. One of the things that you need to realize is that the force actually represents what we call the net force. So you can look right here, you can say I've got 50 newtons up, 50 newtons down, those cancel each other out. I've got 100 newtons right, I've got 20 newtons left. Those don't quite cancel each other out. So what I can say is that my force is 80 newtons, because you have one force to the right, one force to the left. Now, I'm going to assume that the object is actually moving in the same direction. Really, it should say, and it moves 10 meters to the right. So that lets me know that my distance or displacement right here would be 10 meters. I can use my equation work equals force times distance, and I can say 80 times 10 is 800 joules. Okay, so you need to be able to use everything that we've already talked about in terms of free body diagrams, identifying what the force actually is that's being exerted on it, because those things don't go away. In the second example, it says determine the work done on a car. It's got 1,000 kilograms, so we're going to underline what we've got. If it accelerates at 5 meters per second for 25 meters. Okay, and you may be looking at yourself saying, okay, I'm trying to find the work, and then say, once you know that what you're trying to find, you look at what you're given. We're given a mass of 1,000 kilograms. We're given an acceleration of 5 meters per second squared. We're given a distance or displacement of 25 meters. And what we're trying to solve for is once again the work. So you look at your equation, you say work equals force times distance. You say, okay, well, work equals force times distance, but I don't have the force, so I can't solve this question. And this is another case of you have to remember what you were taught before. So yes, you do not have the force, but you learned earlier that you had an equation that said that force equals mass times acceleration. If force equals mass times acceleration, I can substitute ma in for F. And what that does is it gives me a new formula. W equals MAD, or I like to remind my students that it just says that work makes you mad. It's an easy way for you to remember, work makes you mad. So whenever you do this, you can now plug in the numbers and you would say, okay, work equals 1,000, which was my mass, times 5, which was my acceleration, times d, which was 25, which was my displacement. Whenever you take all this and you multiply it out, you should get something around 125,000 joules. One of the things that I want you to realize off the bat is the unit of energy, the joule, is actually an incredibly small amount. So when you see something like 125,000 joules, don't get nervous and say, wow, where did I get that from? A joule is a very, very, very small unit of energy. For this third example, it says calculate the force exerted on a box when it requires 500 joules to move the 10 kilogram box a total of 25 meters. So in this case, we're trying to solve for the force. Whenever you look at it, you can say, okay, well, I'm trying to solve for the force. And what I have is I've got this 500J, 10 kilograms, and 25 meters. So I would say work equals 500 joules. I would have mass equals 10 kilograms. I would have distance equals 25 meters. And you can say W equals FD. Once again, this is one of those cases in which you can go ahead and solve for it right away. People say, well, wait a second, what is this 10 doing here? I don't know what to do with that. It's actually irrelevant to the question. It makes no difference that you have the mass of the box. All you need is the work, which you can plug in, equals force times 25. Sometimes people get nervous the fact that they have too much information and that they're not solving it the correct way. A lot of times you're given extra information to see if you know what to do with it. So when you take this and divide it out, you would get the force is equal to 20 newtons. Okay. Now, if you wanted to, you could then take the force and the mass and solve for the acceleration, but that's not what the question asks us to do. It asks us to solve for the force.